Johnny here, welcome back to the AHA method. Today we take on one of the most famous equations in all of mathematics, the Basel problem. Add up 1 over every square number 1, plus 1 over 2 squared, plus 1 over 3 squared, and on forever. Can you guess what this endless sum comes out to? Today we'll pin it down, using a slightly different and rather surprising approach. Here's the case, dated 1735. It's called the Basel Problem, after a little Swiss town. The sum clearly climbs to about 1.645, but to exactly what? This defeated Europe's greatest minds for nearly 90 years. Then a young genius found the answer, pi squared over 6. It's correct, yet it feels impossible. How can a plain sum of fractions summon pi? Tell me in the comments how familiar you are with this equation and how you'd approach it. Pause the video and give it a real thought before we go on. For a case this deep, I need the man who first cracked it. All the way from the town of Basel, please welcome Leonhard Euler.
Thank you for inviting me, Johnny. First, a quick warm-up for everyone watching. Look at this sum, but forget the squares for a moment. What if the exponent was something else? What happens if we drop the power to 1 or push it up to a cube? Change that little exponent and the answer changes completely. Hold that thought. Now let me solve today's puzzle a very different way. Take a string stretched from 0 to 1 and nail it down at both ends, just 2 fixed points. Between them lay a loose string. Now grab it at a point and give it a nudge, then let it jiggle freely, shake it completely at random. A smooth, random path, pinned at both tips. We call it a Brownian bridge. Now one simple question. On average, how much does this string wiggle? The single number we'll chase is the average of its height, squared. The bar just means averaged. That one number holds the whole secret, and we'll compute it 2 completely different ways. First, what is a random string exactly? Build it one tiny step at a time. At each instant, flip a coin, heads, step up, tails, step down. Start at 0 and let it stagger. This is a random walk. Call its height at time t, w of t, because every step is independent. The wobbles pile up, so the typical distance it strays from 0 grows steadily with time. Its spread, the variance, at time t is exactly t left alone. It ends somewhere random, almost never back at 0. But our string must be pinned at both ends, 0 at the start and 0 at the far end. The walk already starts at 0, we just need to bring its far end back down. So draw the straight line from the start to the walk's end point. That's the drift, t times w of 1, and subtract it. It's a straight line simply because it rises steadily from 0 to w of 1. Watch, the whole path tilts down and lands exactly on 0. What remains, b of t equals w of t minus t times w of 1, is our bridge pinned at both ends. So how much does our string actually wiggle at each point? Forget the algebra, let's just watch. Here are many random strings at once, every single one pinned at the same 2 ends. Watch closely. Right beside each pin, every string is pulled tight to 0. There's barely any room to move. But out in the middle, far from both pins, they swing wide open. So the wiggle is tiny near the ends and largest in the middle. Trace how big it typically is across the string, and you get a smooth arch. 0 at both pins, tallest in the center. Work it out, and that arch turns out to be exactly t times 1 minus t. But why exactly t times 1 minus t? Here's the lovely reason, and it connects straight back to our random walk. Ignore the right pin for a moment. From the left pin alone, the walk reaches our point after time t, so just as we saw, its spread is exactly t. Now bring the right pin back. It reels the whole string back down to 0, and here is the key. The closer our point sits to that pin, the harder it gets reeled in. The freedom the right pin leaves behind is simply the distance to it. 1 minus t, so the spread we started with, t, is cut down by that factor. T times 1 minus t, and right in the middle, both pins are far away, so the string is freest, which is exactly where it wiggles the most. One caution, t times 1 minus t is not a single string. It's the average over countless random strings of the height squared at each point. The randomness has been smoothed into this parabola. Now take one more average across the whole length. The area under it from 0 to 1 is 1/2 minus 1/3, exactly 1/6. So, tallied by position, our number is 1/6. Hold on to it. Now for something completely different, a second way to describe the very same string built entirely out of waves. So first, what exactly is a wave? Here is a simple sine wave with its crests and troughs. Every wave follows one tidy formula, y equals a times the sine of f times t, with just two ingredients. The amplitude, a, is how tall its crests rise above the center line. And the frequency, f, is how rapidly it oscillates as you move along. A short cycle means a high frequency. Now remember, our string is nailed to 0 at both ends. The lowest, simplest wave that fits, rising from 0 and settling gently back to 0, is a single smooth arch. Its formula is a times the sine of pi times t. This is the first harmonic. Our first harmonic, that single arch, is far too crude to match this jagged random string. So we add the next harmonic, the sine of 2 pi times t, which makes two humps. And here is the principle of superposition. The two waves simply add together, point by point. Then we fold in the third harmonic, the fourth, and so on. Watch the running sum. With every new wave we add, it hugs the target string more and more closely. And here is the beautiful fact. Any shape pinned at both ends is exactly a sum of these harmonics, each with its own amplitude. Add enough of them, and the string is rebuilt perfectly. One last tidy detail before we start shaking. We will scale every harmonic by the square root of 2. Why bother? Because what we really care about is each wave's energy, and energy simply means the average of its height, squared, along the string. So take our scaled wave and square it. The result wobbles between 0 and 2, and its average works out to exactly 1. So every scaled wave carries precisely 1 unit of energy, a clean, standard size that keeps every sum still to come beautifully tidy. Now how fast does each harmonic wiggle? Watch closely. Harmonic 1 makes a single half-turn as it crosses from 0 to 1. Harmonic 2 makes two half-turns, harmonic 3, 3, and harmonic 4, 4. So harmonic n makes exactly n half-turns. And here is the key. One half-turn of a sine is worth pi. So n of them give n times pi, and that is the frequency of harmonic n, and there it is at last, pi itself, hidden quietly inside the waves. Now at last, let's actually shake the string, completely at random. A truly jagged, random shake is what physicists call white noise, and it does something remarkable. It gives every single harmonic its own independent, random amplitude. We'll call the random amplitude of harmonic n z sub n, and here is the crucial part. White noise treats every harmonic equally. No note is favored over another. So each z sub n is a fresh random number, all sharing the same typical size, 1. It simply records how much of harmonic n happens to show up in this particular shake. But here is the one deep fact, and a real string behaves exactly like a guitar. Pluck a guitar and you don't hear a single pure note, you hear a whole stack of harmonics ringing at once. Yet the higher, faster harmonics always come out fainter. It is the same for our string, it resists fast waves. So each harmonic's random kick, z sub n, gets divided by its frequency, n pi. The amplitude of harmonic n is therefore z sub n. Over n pi, the faster the wave, the weaker it sounds.
So the quick, high harmonics are the quiet ones, exactly like the faint overtones on a guitar string.
Perfect, so now let's put every single wave back together, each harmonic carrying its own amplitude, z sub n over n pi. Watch them stack up one upon another. And there it is, the complete jagged random string rebuilt entirely out of waves. It is the very same string we began with, only now written as one grand sum. B of t equals the sum over every n of z sub n over n pi times root 2 sine of n pi t. Now each harmonic carries some energy, and energy is just the average of its amplitude squared. For harmonic n, that is the average of z sub n over n pi all squared. Since z sub n's typical square is 1, the energy of harmonic n is simply 1 over n pi squared. And because the harmonics are all independent, their energies just add up. So our average wiggle, counted by waves, is the sum of 1 over n pi squared. And here is the tidy part. Pull the pi out of every single term, and that sum becomes 1 over pi squared times the sum of 1 over n squared. the very mystery sum we set out to find at the start. Now let's take a breath and see the whole picture. Our entire quest was to pin down one single number, the average wiggle of the shaken string, and we pinned it down in two completely separate ways. In the first way, we thought of the string by its position, a random walk, pinned into a bridge, and the average of its height squared traced a gentle arch, whose area came to exactly 1/6. In the second way, we rebuilt the very same string out of waves, superposing harmonics, each with its own random amplitude, and adding up their energies gave 1/π² times the sum of 1/n². 2 roads, 1 number. And now the trap springs shut. It is the very same number, so these two answers must be equal. 1/6 equals 1/π² times the sum of 1/n². Now simply multiply both sides by π², and there it is, the treasure we came for. The sum of 1/n² equals π²/6, not pulled from a circle, squeezed out of a shaken string.
Unbelievable. So pi never came from a circle at all. It came from the frequencies of the waves trapped between the two pinned ends.
Precisely, pi was the frequency of the waves living between the pins. The Basel problem has many proofs, but few show you so clearly and so physically exactly where the pi is hiding.
Now the surprise, and it ties right back to today. Pick two whole numbers at random. What's the chance they share no common factor, that their greatest common divisor is 1? Take a moment. The answer is a gorgeous cousin of what we just found. One hint. For any prime p, the chance it divides both numbers is 1/p², and different primes are independent. Multiply the chances of dodging every prime, and today's answer smiles right back at you, turned upside down. Here's the deal. Post your answer in the comments with a short explanation. The very first correct solution wins a $5 gift voucher. A huge thank you to Leonhard Euler, and thank you for watching. If a shaken string just conjured pi from thin air and made you smile, hit like and subscribe. Aha you in the next one.